In fluid dynamics, viscosity is a fluid's resistance to flow, essentially the internal friction between liquid layers as they slide past one another. Think water versus honey. Water has low viscosity and flows easily, while honey has high viscosity and resists movement. In automotive coatings, viscosity is a make-or-break property because it controls spray atomization, metallic orientation, leveling, and sag resistance. To understand viscosity properly, we must also understand shear force. Shear force is the force applied parallel to a fluid layer that causes one layer to move over another. Whenever paint is stirred, pumped, or forced through a spray gun, it is under shear. Viscosity describes how strongly the paint resists this shearing motion. High-viscosity coatings resist shear and need more force to move, while low-viscosity coatings shear easily and flow with less resistance. There are two fundamental ways viscosity is defined. Dynamic viscosity measures the actual force required to shear or move a fluid. It tells us how much resistance the paint offers when it is being stirred, pumped, or sprayed. Kinematic viscosity, on the other hand, is dynamic viscosity divided by density and describes how a fluid flows under gravity alone. In simple terms, dynamic viscosity answers, how hard is it to move this paint? While kinematic viscosity answers, how fast does this paint flow by itself? Most automotive coatings are non-Newtonian, meaning their viscosity changes with shear rate. If you plot viscosity on the vertical axis and shear rate on the horizontal axis, you get a downward sloping curve. At low shear, such as inside a flow cup or when the paint is sitting in a pot, the viscosity is high. As shear rate increases, inside a pump, hose, or spray nozzle, the viscosity drops. This behavior is known as shear-thinning, and it is intentionally engineered into modern coatings. This shear-thinning curve is the reason paint can spray easily but still stay where it lands. Under the high shear of atomization, viscosity drops, improving droplet breakup and spray transfer efficiency. Once the paint hits the panel and shear is removed, viscosity recovers, helping prevent sagging and runs while allowing controlled leveling. On the shop floor, viscosity is often measured using gravity flow cups, which operate at very low shear and therefore reflect kinematic style behavior. The Ford cup, standardized under ASTM D1200, is widely used. When we say Ford cup number 4, the FR refers to the orifice diameter, not the viscosity value. A Ford cup number 4 is designed for medium to high viscosity coatings, typically producing flow times between 20 and 100 seconds at 25 degrees Celsius, covering most base coats, clear coats, and primers. The Zahn cup is a dip-style flow cup used for quick, low-shear checks, best suited for low to medium viscosity materials in the 15 to 60 second range. In Europe, the DN cup is common, while the ISO cup is the international reference. The ISO cup's longer orifice creates more stable laminar flow and slightly higher effective shear, allowing accurate measurement across a broader range, typically 10 to 200 seconds, depending on cup size. Importantly, cup numbers are not interchangeable across standards due to differences in geometry and shear conditions. For moderate shear measurement, the Krebs viscometer, also called the Stormer viscometer, is widely used in production. A paddle spindle rotates at a fixed 200 revolutions per minute, and the resistance is reported in Krebs units or KU, typically between 40 and 140 KU. This method reflects dynamic viscosity behavior during mixing and application preparation. For high shear analysis, the cone and plate viscometer is the gold standard. It applies a precisely controlled and uniform shear rate across a tiny paint sample, allowing engineers to directly observe how viscosity changes across the entire shear rate curve. This is critical for predicting spray gun behavior, atomization quality, and film build under real application conditions. Shear behavior is also directly linked to appearance defects. If viscosity drops too quickly under shear, metallic flakes can overorient, leading to poor metallic flop and light-dark shade variation. If viscosity recovery is too slow after application, flakes may move randomly during solvent evaporation, causing mottling or clouding. On the other hand, if low shear viscosity is too low, the coating may not hold its shape on vertical panels, resulting in sagging and runs. This is why rheology additives are carefully balanced to control low shear viscosity for sag resistance, mid shear viscosity for leveling, and high shear viscosity for sprayability and metallic control. From low shear flow cups to moderate shear Krebs measurements and high shear cone and plate analysis, each instrument reveals a different part of the viscosity-shear relationship. Understanding how kinematic and dynamic viscosity interact with shear rate is the key to getting smooth application, stable metallic orientation, and consistent appearance on the vehicle. From low shear flow cups to moderate shear Krebs measurements to high shear cone and plate analysis, each tool reveals a different side of how paint behaves in the real world. When shear behavior is correctly balanced, you get easy spraying, controlled leveling, proper metallic flop, and excellent sag resistance, resulting in a flawless automotive finish. Now I'd love to hear from you. Have you faced issues like metallic mottling, shade variation, or sag that you later realized were viscosity or shear related? Drop your experience or questions in the comments, and let me know which topic you want to dive into next.